So now we're moving on to the conservation of linear momentum. Now I actually should have specified what momentum is before this, but it is essentially just the product of mass and velocity. So that's all momentum is, but the conservation of momentum sort of runs a bit like the conservation of energy. So the conservation of linear momentum says that in a closed system, the momentum is conserved. So the archetype for this is kind of a car crash. So if two cars are traveling, I'll draw a little sketch. So if two cars are traveling and they have momentum P1 and P2, P is the symbol for momentum, and they travel towards each other, when they crash, the momentum is going to be conserved. So in general, the formula reads that the change in momentum initially is the same as the change in momentum after, or the net momentum after. This can be read as the change in momentum for the first object is the same as the change in momentum of the second, which can be written as m1 times u1 plus m2 times u2 equals m1 v1 plus m2 v2. So the mass of the first times the initial velocity of the first plus the mass of the second times the initial velocity of the second is the mass of the first times the final velocity of the first plus the mass of the second times the final velocity of the second mass, for masses that aren't entangled. So entangled masses, if we have this car crash for instance, we're going to get like a bit of a mess here. So it's going to become one body and it's going to have one singular velocity, which we label as vc for a common final velocity. Because they have a common final velocity, we can factor out a v, or I should have written v sub c here. So we get that m1u1 plus m2u2, like before, is just the sum of the masses times this common speed. So we're going to go through an example of a non-entangled and then an entangled example just to show how the mathematics of it work.